Once again, welcome to the channel Unknown Warrior. Today we are going to see the part third of the types of curve in computer graphics. So we have already studied fractional representation curves in previous lectures, in which we have studied Hilbert curve and Koch curve. And in first part we have seen two concepts, that is interpolation and DDA for arc generation and interpolation for the curve generation. So today we are going to see the second type of curves. Those are spline curves representation, in which there are again two types of curve. Those are Bezier curve and B-spline curve. In today's session or lecture, we are going to see introduction to the spline curves representation and Bezier curve. Okay, so let's begin. So first, the term that is spline curves was from the concept of drafting, in which drafting means nothing but the graphical representation of some object or things. So the draftsman used flexible strip which bends in the direction of the weight. As you can see in the following figure, here architects or the automobile company draftsmen use this flexible strip which consist of weights which are in the shape of like ducks. So the curve bends in the direction of that weight. As you can see in this, the flexible strip bends towards the attached weight. Similarly, in second diagram you can see the weights are shown. Okay, those are nothing but known as what, ducks, and the curve represents spline. So as you can see, the spline or the curve bends towards the attached weight. So this is how the term spline curves was formed. Next concept is, we have already gone through it, that is the interpolation and approximation in previous videos or lectures. So in this, the interpolation method means the curve passes through each control point, whereas in approximation, first and the last point is the only ones through which the curve passes through, whereas the other points we draw the curve by taking the approximation. Here the spline curves representation uses approximated method, whereas the fractional representation curves, that is Hilbert and Koch, use interpolated method. So today, as we are seeing the Bezier curve, the focus will be on approximation of the control points, in which the curve passes or interpolates the first and the last point. Okay, so this was nothing but interpolation and approximation. So type and shape of the spline curve depend on basis function. The basis function is also known as blending function. We have discussed this blending function in the previous lecture, and boundary conditions. So first we are going to see the Bezier curve in spline representation. So Bezier curve was invented by Pierre Bezier. So they are mostly used in engineering designs and CAD packages. As we have already gone through that these spline curves, and now Bezier curve uses approximation technique for drawing the curve. In Bezier curve, the degree of the polynomial function is always 1 less than the number of control points. As you can see in the figure given on the screen, if for example this shape, we are having 3 control points through which we want to draw the curve, then the degree of the polynomial function of this curve will be 2. Similarly, for the second figure, if the control points are 4, then the degree of the polynomial function for this curve will be 3. Similarly, the control points are 5, then the degree of the polynomial function will be 4. So these were the basic concepts related to the Bezier curve. Basically, polynomial means the expression consisting of variables coefficient. So let's see that how the polynomial functions can be formed for drawing the Bezier curve. So first of all, we start with the control points. So if the degree of the polynomial function is 3, so basically there are 4 control points. So with n plus 1 control points, the parametric equation of Bezier curve approximation points P0 to Pn is, so the parametric equation P of t can be formulated using the formula summation I ranging from 0 to n Pi Bz t. So here the Pi is nothing but the control point and Bz is nothing but the blending function of Bezier curve, taking the parameter as t, where t ranges within 0 and 1. So how this blending function of Bezier curve can be formulated? So it can be formulated by using the Bernstein polynomial. These Bernstein polynomials are as shown on the screen. So the blending function can be calculated as the binomial coefficient, that is c of n comma I, is nothing but the binomial coefficient into t raised to I 1 minus t raised to n minus I. This binomial coefficient can be calculating using the following formula, that is equals to n factorial divided by n minus I factorial into I factorial. So basically what we have to find is the parametric equation which has this blending function. Blending function can be formulated or calculated by using the given formula, in which the binomial coefficient can be calculated as shown. After finding these parameters, we have to find the equation, Bezier curve equation in each direction. So for that we can use the below formula, where for each direction means we have to find x of t, y of t and z of t. The curve can be in 2-dimensional or as well as in 3 dimensions. So to do that, we are going to form the equations. So for calculating the Bezier curve equation for x direction, we have the formula as again summation ranging from 0 to n xi into blending function where t ranges from 0 to 1. Simply what we are doing here is we are putting p in parametric equation as x. So by using the parametric equation as shown in the first expression, we are calculating the Bezier curve equation in each direction, where we take p and x and y and z. And we know how to calculate the blending function, and in blending function how to calculate the binomial coefficient. Okay, so by using parametric equation, we have found the Bezier curve equation in each direction. Simply just we have replaced the value of p by the x, y and z to calculate the equation in x direction, y direction and z direction. So what are the properties of Bezier curve? So first property, as we have already discussed, that the degree of curve is 1 less than the number of control points. That is, if the control points from which we have to draw the curve is 4, then the degree of the polynomial function will be 3. It always interpolates first and the last control point. This also we have already discussed, that it uses the approximation method, so the curve passes through the first and the last control point. That is, it interpolates the first and last control point, whereas it approximates the remaining points so as to form the smooth curve. Do not have local control, that is, if we change any one control point of in the curve, the whole shape and size of the curve gets changed. At any parameter value of t, sum of all Bezier blending function is always 1. So these were the 4 properties of Bezier curve. And we have already seen the application of Bezier curve. Basically, Bezier curve method or technique is used in computer graphics, animation, engineering design, modeling, design automobile parts, and graphics packages like Photoshop. So here Bezier curves consist of 2 solving methods. So first one is cubic Bezier curves and second one is subdivision method. So let's see first how we can form the curve using cubic Bezier curves method. So in cubic Bezier curves are the bridge between computation cost and smoothness. So let's consider, as it is a cubic Bezier curve, so there are total 4 control points. So consider 4 control points to generate cubic curve. That is, the degree of the polynomial function will be what? 1 less than the control point size. So it is n equals to 3. That is degree equals to 3. Okay. And here the control points will range from 0 to n, which are represented by the variable I. So n, that is degree equals to 3, and control points, that is I, will range from 0 to n for the formation of the curve. Then the blending function seen previously for cubic curve will be converted in. So we have already seen the blending function formula for the Bezier curve. So by putting the value of n equals to 3 and I from 0 to n, we get total 4 blending functions or the polynomial functions to draw the curve. So these are the four blending functions for I equals to 0 and n equals to 3, for I equals to 1 and 3, 2 and 3, and 3 and 3. So basically, if we put the value of I in this formula as 0 and n equals to 3, the resulting expression will be 1 minus t raised to 3. Similarly, if we put I as 1 and n as 3, then the resulting expression will be 3t 1 minus t raised to 2. Similarly, for 2, 3, it is 3t raised to 2 1 minus t, and for 3, 3, it is t raised to 3. So, how we can get the matrix representation for the cubic Bezier curve? So, let's focus on the parametric equation as we have seen it in previous while studying the Bezier curve. So, here is the parametric function, that is p of t. We have seen this formula before. So, what we put here is the values which we have calculated, that is nothing but the blending functions of the cubic Bezier curve. We are going to replace them in this formula. So we are taking here I ranging from 0 to n, and n, as we have already known, that n equals to what? 3. So first of all we are going to put I is equals to 0. So we will get here p of I, that is nothing but p of 0. And for blending function, that is bz, I is 0, so we will get bz 0, and n is nothing but 3. So here we have taken 3t, and so on, by putting the value of I equals to ranging from 0 to 3. So p0, p1, p2, p3, and all the blending functions of I, n. So we have already formed the expression for the blending function for point 0, for point 1, point 2, and point 3, and those are replaced in the function. So for blending function 0, 3, we are having the expression as 1 minus t raised to cube. So we have replaced this blending function by the expression 1 minus t bracket cube. Similarly, blending function for 1, 3 as 3t 1 minus t square, which we have got by putting the value of I equals to 1 and n equals to 3 in blending function of the Bezier curve. So after putting this all values, we have finally got the expression from which we can form the matrix. So as you can see here, the 1 minus t raised to cube. So by using the mathematical expression as x minus y raised to cube, we can expand the bracket as shown. That is, expansion of the bracket 1 minus t raised to 3 will be 1 minus 3t plus 3t square minus t cube, and p0 as it is. So we have just expanded the brackets and formed the final expression through which we can form the matrix for cubic Bezier curve. So the parametric equation in matrix form is as shown. So parametric equation P of t equals to row matrix consisting of t cube, t square, and t1, where t ranges from between 0 to 1, and the matrix is formed by taking the columns as the expression. And here, as you can see in the first expression, we are having the constant for point 0 is 1, minus 3, 3, and minus 1. So we have put the constant in the matrix as minus 1, 3, minus 3, and 1. Okay, so here we are taking the highest degree constant first. That is, here the highest degree is what? Minus 1. So we have put here minus 1. Then the constant of the second highest degree, that is degree 2, is 3. So here we have written here 3. Then the degree 1 is minus 3. Then constant minus 1. Similarly, for the second expression, we are having constant for the degree 3 as 3. So we have written 3. Then constant for the degree 2 as minus 6, and constant of the degree t as 3, and as there is no only constant, so we have considered it as 0. Similarly, for expression 3, t cube has having the constant as minus 3, so we have put here the value minus 3. T square has the constant 3, and there are no other parameters mentioned in this expression, so that's why we have taken here 0, 0. Similarly, for last parameter, we are having only t cube, and the constant here is 1. That's why we have put here 1, and there are no other parameters, so we have considered here 0, 0, and 0. So for each expression which is formed in above, as above, we have taken the constants of each expression and ranging from degree 3 to 0. So this is how we form the expression. Okay, or this is how we have formed the matrix by using the above expression. And into, as we are having here pt into, that is pi, so we have considered here matrix which is p0, p1, p2, p3 values. Okay, so we get the final matrix as p equals to t into m to the base bz into g to the base bz, where m and g are nothing but the matrix, where m is matrix known as Bezier basic matrix and g as Bezier geometric matrix. So this is nothing but Bezier basic matrix, and this is nothing but Bezier geometric matrix. So this is the final matrix representation for the cubic Bezier curve. So basically there are many problems we can solve which are based on the Bezier curve, and and by using any of the two methods, that is cubic Bezier curve or subdivision Bezier curve, we can solve those problems by using the matrix representation of any of the two methods. So second method is subdivision method. So here, as the name itself tells us, that subdivision means we have to divide something into some parts. So basically what is in the subdivision method? So this method generates a Bezier curve by simply midpoint calculation. So let us derive Bezier curve defined by the control points as shown in the figure P1, P2, P3 and P4. So join the consecutive control points using the straight line. So we have drawn the line from P1 to P2, P2 to P3 and P3 to P4. Next is, suppose that the midpoint of the line P1, P2 is L2, midpoint of the line P2, P3 is H, and midpoint of the line P3, P4 is R3. Then what we are going to do is, we are going to join the point L2 and H and name its midpoint as L3. Then we are going to join the line H and R3, and we are going to name its midpoint as R2. Similarly, join point L3 and R2 and name its midpoint as L4, where L4 is equals to what? R1. Similarly, we have considered P1 equals to L1 and P4 equals to R4. And iteratively, we are doing the breaking and subdividing the line segments to form a smooth curve. So basically, recursively draw the two Bezier curve segments between control points. So we are drawing the two Bezier curve segments between the control points. So the left hand side Bezier curve is passing through the point L1, L2, L3 and L4, and the right hand side Bezier curve is passing through the point R1, R2, R3 and R4, where the common point is L4 and R1 in both the Bezier curves, and both these Bezier curves are what? Independent. Okay, so number of recursive calls decide the smoothness of the curve. So as you can see in the diagram, first of all we have considered the line segments between the point P1, P2, P3, P4. Then we have taken the midpoint of line L2, H and H of R3, and then we have taken the midpoint of line L3 and R2. Why we are iteratively breaking down the line segment is to get the final smooth curve. So this is the goal of the subdivision method, that is to form the curve which is smooth. So our goal is to find the polynomial function for the left hand side Bezier curve and right hand side Bezier curve. And finally, we are generating two matrices for left hand side Bezier curve and right hand side Bezier curve. As I have already told you, that both these curve segments are independent Bezier curves. So let's see what are the polynomial functions for the left hand side curve passing through the points L1, L2, L3 and L4, and the right hand side curve passing through the points R1, R2, R3 and R4. So to generate the left hand side curve, we need to find the expression for points L1, L2, L3 and L4. And similarly, for generating the right hand side curve, we have to find the expressions for point R1, R2, R3 and R4. So basically, totally to form the complete full curve, the curve passes through the 8 points. So there are 1, 2, 3, 4, 5, 6, 7. But as both the Bezier curve are independent of each other, so that's why we have put 8p1 divided by 8. So L1, that is nothing but equals to p1 equals to 8p1 divided by 8. Similarly, L2 is equals to, as L2 is the midpoint of line P1, P2, that's why we have written the formula as P1 plus P2 divided by 2. And that is equals to, as we have to show that the curves are formed between 8 points, that's why we have converted this expression into 4p1 plus 4p2 divided by 8. That is, we are dividing both numerator and we are multiplying both numerator and denominator by 2. Then similarly, H is the midpoint of point P2 and P3, that's why we have written this expression. Similarly, L3 is the midpoint of line L2 and H, that's why L2 plus H divided by 2, that is nothing but L2 is the midpoint of P1 and P2 divided by 2. H is the midpoint of P2, P3, that's why we have written P2 plus P3 divided by 2. So this is the expression for L2, and after some conversions we get the L3 as 2p1 plus 4p2 plus 2p3 divided by 8. So here we can see that all the L values are having the denominator set as 8. That's why we are converting the expressions such that the denominator becomes 8. Now as we have calculated L1, L2, L3, okay, then L4 is nothing but equals to R1. So that is equals to L3 plus R2, as R1 is R1 or L4 is the midpoint of line L3 and R2. So that's why the expression is L3 plus R2 divided by 2. Then again sum of the conversions, we have found the expression for L4 and R1 as P1 plus 3P2 plus 3P3 plus P4 divided by 8. So as we have found L1, L2, L3 and L4 point expressions, so we can form the left hand curve easily, where as we have seen in the previous figure that L4 and R1 are equals. That's why the expression for R1 is same as L4. Then R2 is nothing but the midpoint of H plus H and R3 segment. So we have formed the expression as H plus R3 divided by 2. And we have formed the final expression. So sorry, here I have mistakenly written here 4. It should be 8, as we have to convert each expression into 8. That is, we have to make denominator as 8. So we have multiplied this expression, that is numerator as well as denominator, by 2. So we will get this expression, that is 2p2 plus 4p3 plus 2p4 divided by 8. Okay, so this is nothing but the expression for R2. Similarly for R3, R3 is the midpoint of line segment P3, P4. So this is the expression, that is R3 is midpoint, so P3 plus P4 divided by 2. So we are again converting the denominator into 8. So that's why we are multiplying both numerator and denominator by 4. Okay, so we get the expression as 4p3 plus 4p4 divided by 8. Similarly R4 is equals to P4, that is equals to 8p4 divided by 8, as P4 and R4 are the points which are what, end points of the curve. So that's why they are only having point P4. So to make the denominator 8, we are multiplying and dividing the P4 by 8. And as L1 or P1 is the starting point, we are dividing to make the denominator as 8. So we are multiplying and dividing the P1 by 8. So I think you have understood how to calculate the expressions for each point, that is left hand to draw the curve, left hand side curve, and to draw the right hand side curve passing through the points. So total there are 8 points. That's why we are making the denominator as 8. And to form that, we are doing some changes in the expression. So we have got the expression for L1, L2, L3 and L4. Those are the points through which the left hand side curve is going to pass. Okay, and we have found the point R1, R2, R3 and R4 through which the right hand side curve is going to be passed. So as we have seen that these two curve segments are independent of each other, therefore there are independent matrix for each curves. So the matrix for the Bezier left subdivision matrix is as shown below. So here G to the base b and raised to L equals to, so here GB raised to L is nothing but the Bezier left subdivision matrix. So it is calculated by dBL into GB, that is equals to 1 by 8. Okay, and we have taken here the matrix. So here the matrix is nothing but as shown above. So the columns consist of the points P0, constants of the point P0, P1, P2, P3, and the row consists of the points L1, L2, L3 and L4. That is, we are going to consider the expression for the points L1, L2, L3 and L4, in which the constants of the point P0, P1, P2, P3 will be in this sequence. Okay, so let's consider one example to study how this matrix is formed. So as we are for the left subdivision matrix, that is to draw the left hand side curve, we are going to consider the points L1, L2, L3, L4. That is, we are going to consider the expressions for these points. So let's see the expression for L1. So it is 8p1 divided by 8. That's why we have considered here what? 8. That is p0 here. P0 or P1. Sorry, I have written the P0. It is P1 actually. So P1 has the constant what? 8. So here we have taken what? 8. Okay. So 8. Then P1. Okay. As there are no other constants, so we have taken here what? 0. Okay. Next one is we are going to consider the second expression L2. So L2 is equals to is having P1 as 4 and P2 as 4. Okay. So we have taken the constant here P1 as 4 and P2 as 4, and as there are no rest of the parameters, we have considered as 0. Similarly, we will take the third row and the fourth row constants. Okay. So P1 constant will be the first one, P2 constant will be the second, P3 constant will be the third, and P4 will be the last. As this is the L4 expression, so here is the L4 expression in which P1 is having the constant as 1. So we have written here 1. P2 is having 3, so here we have written 3. P3 is having 3, so we have written 3. P4 is having 1, again here we have written 1. Okay, so I think you have understood how we have written here the matrix. I'm sorry for the given showing these parameters is wrong. It is actually here P1, here P2, P3 and P4. Okay, I hope you have understood how we have formed this matrix. Okay, divided by the geometric matrix of the Bezier left subdivision matrix. As we have seen that we have formed the matrix for the left subdivision matrix, similarly we are going to form the matrix for right subdivision or right hand side curve. So by using the expression R1, R2, R3 and R4 and taking the constants of the points in those expressions, we have formed this matrix. So by using this both matrix, we can solve the we can form the Bezier curve by using the subdivision method. So in the next lecture, we are going to see the problem solving in Bezier curve. So either we are going to see the problems which consist of forming the curves by using either subdivision method or by using the cube Bezier curve method. Thank you for watching the lecture. Hope you will subscribe, like and hit the bell icon of unknown word.